QFT Lecture.
All right, so we have the final exam coming up. So, the final exam will cover everything that we've done since the midterm exam. So, basically from the Dirac equation onwards. And it is on Friday, the 4th of May. (7 p.m. to 9:30 p.m. Final exam, Friday the 4th of May. That's right, that's not 7 a.m., that's 7 p.m. to 9:30 p.m. So,
is it possible we could, if we could find another time slot?
So the, all right, so this always comes up. And the problem is, so the first year I was here, I was naive. I thought, well, sure, we'll find another time slot. To find, why should there are only 4 students? But there's always this problem. There's one person who has an exam with some of the others, and there's the room is booked for this, that, and the other. So, but I do take pity on you. I mean, look, what we can do, if you suggest, do you want to try and find another room and another time slot?
So I think since there's only 4, we could either do it in the conference room in the office or the regular conference.
If you want to. So, who have a show of hands? Who would rather we stick to this time? Who would rather we try to find another time? Who votes? Who votes is this man's responsibility? Okay, so I tell you what we'll do. So do you have everyone's email addresses? You sure? You've got your email address? So where are we? Today is Thursday. You know, look, listen, can you let me know, as soon as possible? Maybe, hopefully, you may say by tomorrow. There you go, you've got till tomorrow. Okay, please email me tomorrow. If you can't find another room, then, this is the time slot and it's in here. If you can find another place, so let me think, let me see, there's a problem now, do I have other things going on next? So Monday I'm not available. Monday I'm completely not available. Wednesday evening I'm not available. Hang on a sec. And then Indrajit has got his oral. No, hang on, is that next week? No, that's the week after. That's the week after. So next week's exam week, so Monday moving. Yeah, Monday I'm not available at all, and Wednesday I'm not available. Okay, so let me know, and if we end up having to do it this time, so some administrator somewhere thought it was a bright idea to have an exam Friday evening. If you can find their email address, you're welcome to send them hate mail, and please quote me on that. You're welcome to quote me on that. So one thing about the exam, so there's an oddity here. Please show your working. So there seems to be a different philosophy of exams in the US than what I'm used to from the UK. So in the UK, if we would have got to solve this problem, you just start trying to solve it, you're right there, you try and get to the answer, and then the examiner looks at what you've done. If you've got the wrong answer, but you've got the right method, you'll get most of the marks. Here there seems to be this idea that you just, you do all your working, and then you rub out your working, and then you write the answer and put in a little box. I don't know, did you dream the answer? Did you just remember it? Did you copy it? Did you just guess it? I mean, plus, anyway, I find, please, no rubbing out. Just try to work the problem as far as you can, and I'll read through what you do and make a judgment. And it's not just getting the answer, it's showing that you understand what you're doing, that you have the right method, that And you know, if someone's missed a minus sign somewhere, they end up with the wrong answer. I mean, but you've done everything else correctly, you're basically going to get full marks, as far as I'm concerned. So please show the working. I've sometimes seen people rub out things, and I can just discern on the page what they were doing, and they've done it right. But then they did something wrong, and they've written the wrong answer. You know, and if I hadn't peered, you know, doing forensics to see what they'd rubbed out. Anyway, so please show the working. Okay, so we are on our last lecture. So what's going to be examinable is everything we did up until Tuesday, and you'll need to know that cross-section, like all probabilities, are proportional to the modulus squared of the matrix element. The matrix element is proportional to the Feynman amplitude. So all cross-sections are going to be proportional to the Feynman amplitude squared. And now, because it's so late in the day, we're going to do actual cross-sections today, but I'm not going to ask you on the exam to work out the cross-sections. It's a bit unfair because we're just doing it so late. So basically, if you want, you can just leave now and everything is fine. But those of you who are interested, it's sort of similar to what we did way back when we did the scattering. Remember, we did the scattering of a photon by a free electron, Thomson scattering. It's the same kind of idea. So let's go through how to convert our S matrix element into a scattering cross section. So let us see. Okay, good. All right, so here's what we're going to do. We're going to consider, imagine the following. So we have a two-particle collision, and producing n particles. So let's imagine. So here I'm not drawing a Feynman diagram, just drawing a sketch of, you know, what you might see in the lab. I've got two particles with 4 momenta coming in and meeting in some scattering region, and what's coming out are P1 primed, P2 primed, Pn primed. So I've got 2 particles coming in, n particles coming out. These particles can be photons, electrons, positrons, and so on. Okay, so blah, 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 blah. Now, what do? And again, we're suppressing the polarization and spin labels. All right, so now we have our our expression for the S matrix element from the initial to the final state. So let's leave off the Kronecker delta term. We'll assume the initial and final states are different, so the Kronecker first term is 0, and we just have 2 pi to the 4th delta 4th. We have the sum over the final momentum, so the total final momentum minus the total initial momentum. And then, for some reason, the book has decided that it's a good idea now to just write so these factors slightly differently. We'll write the product over the initial states, 1 over square root of 2v pi, product over final states, 1 over the square root of 2v prime final, times the product over the leptons. Now what is lept? Hang on. Square root. L, and then times the Feynman amplitude. what is going on here. So this is a product of leptons, i.e. electrons and positrons. So you may remember that the factor is 1 over root 2v omega for photons. And, of course, I've forgotten, I always forget what the damn thing is. So, and square root of m over VE for electrons and positrons. So if you think about it, omega is just the energy of a photon. Okay, so what I can do, I can write this, so I can write this as 1 over root 2VE for, where E is the energy of the photon, and I can write this as 1 over root 2VE times root 2m. Okay, so it's just the same thing. So here we're just, so here I'm multiplying over initial and final states, regardless of whether they're electrons, positrons, or photons. There's always a factor 1 over root 2v energy. The external, if any of these external particles are electrons or positrons, then there are factors root 2 times the mass. And okay, and then times the Feynman amplitude. All right, so now, what do we have? This was derived for an infinite time interval. T going to infinity. Remember, we started with a state at minus infinity, and we go to a state at plus infinity. And for infinite volume, we took the normalization volume to be arbitrarily large. Okay, so there's a bit of hand-wavy stuff. Remember, there's some hand-wavy stuff in the derivation of the cross-section way back. There's similar hand-wavy stuff here, which, well, we'll talk about it a bit more as we go along. But let us say that if we had done, so if we had finite TV, then if you go through the derivation, what we would have had is the delta function would be replaced by something, let's call it delta T, delta 4 TV, some T prime final minus some T initial, where what is this? Where this is defined to be the following integral. T integral over a finite time interval t, and an integral over finite volume v of the following exponential ix sum t prime f minus the sum. That is right. Okay, so in other words, this thing here is equal to the limit as t and v go to infinity of delta 4 tv. Okay, if I take the limit as t goes to infinity, v goes to infinity, I get the delta function. Now, if you go back through the derivation, you say, well, imagine, let's take tv, leave them finite, then you would have this expression, but with the delta function replaced by that term. Now, what we can do is define the transition probability. Transition probability per second. We're going to call it W. Okay, call it W. and W is equal to, so we have the modulus squared of our S matrix element, which is the probability of the transition, the initial to the final state, divided by T. There we go. That is our probability per unit time. Now, what we have is, let's see if I can, okay, let me rough this out. I think it's pretty clear what that is. That is just the usual definition of the delta function as an integral of an exponential, but with finite limits. So now what we can do is, if I take the modulus squared here, I get a factor delta TV for sum P prime F minus sum Pi. I will have to square that factor. Okay, I'm taking the modulus squared. This is replaced by delta TV. I'm going to have to look at the square of this factor. Now, what we can do is say that, all right, here's what you can do. Here's a little trick, which is a bit sort of hand-waving, but the result is correct. So here, you can write this as follows. I always find this a bit fiddly. Best way to do this. Okay, what we can do is say, this is approximately here I've got one factor, delta TV, times the other delta TV. If we take TV to be large, and they are large but finite, if T and V are large, then delta TV is approximately equal to the delta function. Okay, so when I square this, delta TV squared, I can say that delta TV squared is equal to delta TV times delta TV, which is approximately delta TV times the delta function. Okay, so, all right, so far. Now, the delta function is non-zero only when the argument is 0. So this is equal to delta 4 TV of 0. Okay. I have to put the argument here equal to 0. And delta TV at 0, if I evaluate that integral, which of course I've just rubbed out, but it's the integral over finite limits of the exponential, then you find that that integral, sorry, maybe I should, remember we had integral minus t over 2 to t over 2 dt, integral over volume times the exponential. Okay, that's our definition of TV. If the argument of the exponential is 0, then this is just 1, and so this integral is just equal to TV. Okay, so the square of the large TV, the square of delta TV is approximately just TV times the delta function. Okay, and so the errors go to 0 as T and V go to infinity. So now let's, I need more room. Okay, so let's go here, over here, and maybe here I can put times the Feynman amplitude in there. All right, so we've defined W to be this expression here, so we take the modulus squared of this and use this. So here we've replaced this by TV. Now for finite TV, we take the modulus squared We're going to use this for very large TV, and so you find that the transition rate, so the transition rate, which is the probability for going from the initial to the final state per second, the transition rate can be written as V, and you might want to check this, so here I'm going to leave, there'll be a few detailed steps here I'll leave you to check through for homework. The transition rate is V, 2 pi to the 4th, delta 4, sum over P final prime, minus sum over the initial momenta, and we've got the product of the initial, the incoming particles, we've got a product of the final, sorry, there's no square root. Why am I writing the square root? I'm taking the modulus squared. So, 2VEI, 2V E final prime, we've got a product over the leptons, factors 2 times the mass, times the modulus of the Feynman amplitude squared. All right. In fact, I wanted to remind you, I said it last time, I want to remind you, so in the final exam, you'll be provided with a list of Feynman rules for QED, okay? It was going to be quite late in the course when we did it, so anyway. All right, so this is the transition rate, this is the probability per second going from the initial to the final state. Now the usual business to find so when you measure, so a realistic detector is going to accept momenta in some small but non-zero range. So as usual in these things, as you've met before in quantum mechanics, and as we did when we did the scattering way back, or when we did an atom emitting a photon, is you look at the transition rate to final states. In the ranges. So you've got D3, D1 prime, D3, D2 prime, D3, Dn prime. So you have n final particles, so the final momenta, we think of them as being in some small range. And what is the number of states? We have to multiply W. So we have to do W times the number of states in the range. So in this interval in momentum space. And as usual, remember we've got V is finite. And remember the momenta restricted to be those values. The momenta of 2 pi over L times a triplet of integers, where V is L cubed. So you count the number of states. So the number of states in this range, this number of states is equal to the product over the final momenta D3 P F prime divided by 2 pi cubed. Just the same expression we saw, I think, before when it was the final photon. We had V D3K over 2 pi cubed. Remember we had a photon scattering off an electron. This was the number of states in a little interval D3K. It's exactly the same thing. And there is also now the question of the incident flux. So let's just remind you that d sigma, if in an actual lab, I'm sending in some particles and particles are coming out, and how do I measure the cross section? What is the cross section? D sigma is the number of events that come out in, let's say there's one solid angle element. If there are many particles, there might be many elements, but just schematically here, the number that come out in some little range of solid angle per second divided by the number incident per square centimeter per second, or per unit area per unit time. But let me just take centimeters and seconds. So the number going into the omega per second divided by the number incident per square centimeter per second. Now what I can do, I can write this as the probability that is going into d omega per second divided by the probability that is incident per square centimeter per second. Now if you think of this, imagine I'm doing one experiment. If I do many experiments, let's say n trials, so I would do times n trials at the top, times n trials at the bottom. Probability times the number of trials is the number, the large n is the number that will actually be realized. So anyway, this is the same thing. So this is what you'd measure, number of events, you'd count them. This is what you'd actually measure, but theoretically it is a ratio of probabilities. Now what we have here is if we multiply W by the number of states in this range, that is the probability per second going into that range. So we've got the top part. Okay, so let's leave off here the number of trials. So we've got the top part. Okay, the top part is done. The numerator is just W times this. So this is equal to the numerator. Okay, so what about the denominator? The denominator, I'm afraid there is the same BS that we had. Remember I introduced this technical term, BS, stands for bad statements. So the incident flux, in other words, the denominator there, the incident flux is the probability, the incident probability per square centimeter per second. So in other words, let's say is the denominator. There we go. The denominator here, the incident flux is equal to the relative velocity. Remember, we have two particles colliding. VRel is the relative velocity of the colliding particles. Now remember, we've seen that, well, hang on, there are no particles moving in quantum field theory. What is this about? So what this is about is, if you imagine that I have so we have so in the volume V, there's one scattering center and one scattering particle. Okay, I've got two particles, you can call them one the scattering center, one the scattering. Anyway, I have two particles that are scattering off each other, and there is one, the way we've defined it, the way we've defined the number operator for these states, one particle state, there's one particle in the volume V. So we'll say, well, okay, so I've got in this large volume V, I've got these two particles in this large volume V. If you were thinking classically, and you imagine that the particle has a probability spread uniformly over this box of volume V. It's in there somewhere, and its probability is uniform. and you ask, well, so what is the if I think of some unit area, say, what is the probability that this incoming particle is passing through this unit area per second? And if you imagine if you say one scattering center is at rest, okay, this is what we had in the case before, we had photons coming in. And you say, well, if I think of an ensemble of photons whose probability is uniform over volume V, and I ask how many photons are coming in per unit area per second. Okay, so anyway, so this is just a simple, this is the answer classically. So anyway, so the probability flux is V relative over V. So this is a lot of BS. There's no foundation in quantum field theory for thinking about it in this way. This is sort of semi-classical. This is what we might call semi-classical reasoning. Now, I've never seen this done. As I mentioned before, I think you could probably do this more rigorously by looking at, for instance, the momentum flow. There is a momentum operator associated with the field. You could probably think in terms of momentum flow and derive this properly. I've never actually seen that done, but so this is how it's usually presented. But this is, if you puzzle, hang on, what is this? What do you mean, particles moving around? That's classical. If this bothers you, you're right to be bothered. This is a semi-classical argument. Anyway, so the denominator here, the probability incident square centimeter per second, is taken to be this relative velocity of the colliding particles, which, given their initial momenta, how do you define the relative velocity? Well, you just imagine if I had two classical particles of those momenta, you can figure out what the relative velocity is. All right, so without further ado, let's just follow and say, all right, so d sigma. What is d sigma? It is equal to W times the product over the final states of V d3 p prime final over 2 pi q. Okay, that is the numerator. That is the probability going into the final little range per second, divided by the incident flux, which is V relative over the volume V. That is our d sigma, and you're welcome to check that this comes out to be 2 pi to the 4th delta 4 sum over p of the final momenta minus the sum over the initial momenta. Remember, I have just two particles coming in. Let's call their energies E1 and E2. I have their relative velocity. I have a product over all external leptons, initial and final, 2m times the mass. I have a product over the final particles. There is a d3 p prime final over 2 pi cubed, 2 e final primed, times the important part, which is the modulus squared of the Feynman amplitude. So this is our expression for d sigma, the differential cross-section into some final range, which I wrote here, range of final momentum states. We have 2 pi to the 4th. There's a delta function for the difference between conserving total for momentum. We have these factors, 1 over 4, E1, E2, V rel, leptons, product over final states. Notice here there's a 2e prime final that's been put in the denominator. And we have mod m squared. So please check. I want to check this. Just go through this, it's pretty straightforward enough. Okay, that is the general expression for a differential cross-section, I have two initial, remember I have P1, P2, two particles scattering to produce many final particles. Now what we're going to do is, let's look at the particular case of where the number of final particles is also just 2. So we have two-body, let's look at the case, two-body in, two-body out. So we're going to have P1, P2, and P1 prime, P2 prime. So, all right, so we're going to need expressions for the relative velocity. Okay, let's see. All right. So what's the relative velocity? So there are two common frames that use the center of mass frame and what's called the lab frame. Whoops. So the center of mass frame. In the center of mass frame, we have P1 is equal to minus P2. Some people call it the center of momentum frame. Anyway, it's the total momentum. So we've got these two incoming particles. The total free momentum is 0. You're in the frame where the total free momentum is 0. In that frame, the relative velocity you can write as mod P1, whoops, the modulus E1 over E1 plus the modulus of E2 over E2. And it's easier to just rewrite this. If you want to check, just simple little bit of algebra, E1 plus E2 over E1, E2. There we go. So there's a useful expression. If you're in the center of mass frame, this quantity here, this relative velocity, what is it? Well, then if I've got this initial momentum P1 and P2, I'm in the center of momentum frame, then the relative velocity is just given by this expression in terms of the magnitude of the momentum and the energies. Okay, in the lab frame, let's go over here and make a bit of space. In the lab frame, what we mean by the lab frame is that the target particle is at rest. So P2, so target at rest. Let's call the target the second particle. So P2 is 0. So I've got one particle at rest and the other particle is fired at it. And in that case, whoops, the relative velocity is just mod P1 divided by E1. Okay, in the lab frame, relative velocity is just, so that's the expression that you would put in here if you're working in the lab frame. Okay, blah, blah, now something. So now let's do we're doing the case we have two particles in, two particles coming out. So energy and momentum are conserved. So So we are given, we're given the initial momenta. Okay, so we're given the initial momenta. There's a constraint on the final momenta. So the final momenta are not independent variables. Okay, we've written a range here like this, which of course for the two-body final case, we're going to have this range, D3P1 prime, D3P2 prime. But P1 and P2 are related by this formula. So what you can do, so in other words, the final momenta are not all independent variables. So what we can do is you can, if you say, well, I'm going to treat one of them, let's say you treat, there you go, let's say you treat P1 prime as your independent. Let's say you have a detector here that's detecting over some range, d omega. Okay, for a given P1 prime, well, P2 is fixed. Okay, so we can eliminate P2 as an independent variable, okay, and write the cross-section in terms of d omega, where d omega is the range for P1 prime. Okay, for a given P1 prime, P2 is fixed by this formula. Okay, simple. So, here's what happens. We're looking at applying our general expression to the case where the final state contains just two particles. So here we go. We can write this. We've got our general expression, d sigma. Let's write it as follows. We've got a function of P1 prime and P2 prime times the delta function of P1 prime plus P2 prime minus P1 minus P2 D3 P1 prime D3 P2 prime, where what is this function? This function here is 1 over 64 pi squared relative velocity E1, E2, E1 prime, E2 prime times the product over these electron mass factors times the modulus squared of the Feynman amplitude. Now you can check through of just rewriting this slightly. So for the case with the product of the final state, there's just two particles, E1 and 2. So you can check that. Simple enough. Okay, now here's the tricky part. So let us integrate. So I'm going to ask you to do this homework check. Okay, that if we integrate with respect to P2 prime. So there's a bit of fiddling. So we've got this delta function, but you're integrating with respect to the spatial part. Remember, there's an energy part here. The energy is written in terms of the momenta. So you've got to think a little bit. If you integrate with respect to P2 prime, you should be able to show the following, that d sigma is equal to f of P1 prime, P2 prime, times a delta function involving only energy times the modulus. Here is the part from D3P1 prime, which I can write as modulus squared of P1 prime, D modulus P1 prime, D omega 1 prime. So here I've written D omega here, but really this is D omega 1, the solid angle associated with the momentum P1 prime. And in fact, we're writing as d omega 1 prime There we go, just to make it perfectly clear. So what we're doing here is writing d31 prime is 4 pi. And what am I saying? Sorry, what am I saying? d3, yeah. Okay, sorry. So this piece here is just d3 p1 prime. Okay, I've just written d3 p1 prime in terms of mod p1 over p omega. Okay, good. So where in this expression, because of the action of the spatial part of the delta function, and we've integrated over p1 prime, this enforces conservation of 3 momentum. So in this expression here, there's a p2 prime lurking in here, where the p2 prime is equal to p1 plus p2 minus p1 prime. Okay, we've integrated with respect to p2 primed, and because of the delta function, in the argument here, p2 primed is now the only value of p2 primed that survives from the delta function is that p2 primed is p1 plus p2 minus p1 primed. Okay, so in the p2 primed that is given. So we've eliminated p2 primed and written it in terms of p1 prime, which is the only free independent variable here. Okay, if we're given p1 prime the range, p2 prime is just fixed by this expression here. Okay, so now what we do is furthermore, and now the really nice bit, furthermore, so more homework for you to do. We now integrate with respect to, so here we continue, we're now going to integrate with respect to expression here, okay, I know what I'm doing, with respect to the modulus of P1 prime. Now we actually did a similar manipulation. If you go back and look at when we derived the cross-section for photon scattering of an electron, we did a similar kind of thing. You integrated with respect to the magnitude of the outgoing wave vector k. This is actually the same kind of thing. If you now integrate with respect to the modulus of P1 prime, so you get rid of this piece here. And of course there's the delta function here. Now it's a bit tricky because remember E1, E is equal to the square root of mod P squared plus M squared if it's a lepton, whereas if it's a photon then it's just the modulus of the momentum. So you have to use that and do a bit of fiddling and use your knowledge of delta function. When I have a delta function of a function, so you should be able to derive the final result, which we're going to do, and we're going to put it in the center of mass frame. There we go. We're going to look. Okay, so all right, let me show you what you should find. What you should find is rub this out because that's clear.
I have a question. For this d sigma that you integrate over p prime, p2 prime, we have a factor m squared?
Sorry, do we have a factor?
Do we have a factor modulus m squared?
If I'm the amplitude should still be on all the d sigmas.
So f is, this function f is defined to be this expression times that squared. So the Feynman amplitude squared is in Just for shorthand, I've written F to be this, well, following the book, just take this expression. This is just some function of the final momenta, so it's just convenient. Okay, so now if you integrate with respect to d1 prime, what you should find is that d sigma is equal to f1 prime, f2 prime, modulus of d1 prime squared, d omega 1 prime, and then there's a little piece here that comes from, remember I've got a delta function that is a function, the argument is a function of the momenta, so you have to fiddle a little bit. This is going to equal the derivative of e1 prime plus e2 prime divided by, with respect to p1 prime to the minus 1. So please check this. Homework. It's pretty straightforward, but there you go. It's a good exercise just to go through that. There's a relation, so the book has got a footnote here. If I have a delta function of a function, and I perform this integral, this is equal to the integral of the function g x y dx by dg, a constant y dg, which is equal to f. I guess it's actually not so trivial already. Anyway, you'll need this dg by dx, the constant y evaluated at g is 0. Okay, there's this general relation. You may have seen something like this before. Anyway, you'll remember that dealing with a delta function of a function, there's some fiddling that goes on. This is the fiddling that you need here to get this. Okay, anyway, go through it, derive this relation, and then we can see now for the case of in the center of mass, frame, where you should be able to show p1 prime is equal to minus p2 prime, and you should be able to show that the derivative p1 prime plus e2 prime divided by, with respect to p1 prime is equal to mod p1 prime e1 plus e2 over e1 prime e2 prime. Okay, you can show that, and we've got our, remember f contains our relative velocity. So we're going to use our relative velocity as well, which we wrote down. The relative velocity is mod P1, E1 plus E2 over E1, E2. Put all this in here, and out pops the final answer. Okay, so d sigma by the omega 1 prime in the center of mass frame is 1 over. So this is for two-body to two-body. 1 over 64 pi squared E1 plus E2 squared mod P1 prime over mod P1 product over the final leptons, sorry, product over the external leptons, initial and final, times the modulus of the Feynman amplitude squared. So just to remind ourselves, so in terms of 3 momenta, let's write just 3 momenta, P1 and P2 coming in. We have 3 momenta, P1 prime, P2 prime coming out. And what we're saying is the initial momenta are given. And so we know that P1 plus P2 is P1 prime plus P2 prime. So if I say, okay, I'm going to look in some solid angle element here, let's call it D omega 1 prime. Okay, I'm looking, I've got a little detector that is detecting where particle 1 comes out. Well, if I'm measuring the direction of the momentum here fixes the other momentum. So these two momenta are not independent variables. So we're treating P1 prime as the independent variable. So we can forget P2 prime. P2 prime is given by this formula. So here is the expression. If we're looking at the probability per second of going into this solid angle element D omega 1 primed, okay, the cross section for this process in the center of mass system is given by this expression. Here are the incident energies. Here is we've got the incident magnitude of momentum, the final magnitude of momentum for particle 1. Here we've just got these mass factors and the modular end. So it's proportional to the Feynman amplitude squared, with some factors in front that depend on the momenta, and of course if I had more than 2 particles coming out, this factor would be a bit more complicated, and the form of it also depends on whether you're in the center of mass frame or in the lab frame. Okay, so a few things to say. In an experiment, you will frequently not be measuring the spins and the polarizations. So, let's see, what did I say? A few things about that. All right. Okay. So in a real experiment, we frequently ignore polarization and spin. So you're just looking at the incoming and outgoing momenta. I may have a beam of particles coming in, they scatter, they come out. I'm just measuring the momenta. So what we have to do is, there's something called, so what you are measuring is the unpolarized cross-section. So what you have to do is average the Feynman amplitude squared that appears in this formula. You have to average over the initial polarizations and spins, and you have to sum over the final polarizations, spins. So I think we did a similar thing way back, but if you think about it, what you're doing, well, I don't know what the initial, so anyway, average m squared over the initial polarization, we sum over the final. So if you think about it, well, the particles coming, I don't know what spins there are, so I'm just going to average over so different particles coming in different runs of this experiment will have different initial spins polarization. So what we're measuring is an average. So you average over the initial ones. Why do I sum over the final? Well, if you think about it, I'm just measuring an event where the momentum comes out this way. Okay, now there are going to be two probabilities for that to happen. There's going to be a probability, say it's an electron, probability that it comes out with this momentum and spin in the direction of the momentum. There's also a probability it comes out with this momentum but spin in the other direction. So the total probability is going to be the sum of the two probabilities. And if I'm just measuring momentum, so there you go. So you have to sum over the final polarizations and spins and average over the. There are some tricks. There are some tricks for this. For example, quite often, when you perform these averages and sums, you'll find that you find terms involving traces of products of gamma matrices. If you're interested, you can look in the book for some examples in chapter 8, but when you do these sums, you often find yourself, there's terms involved. You've got products of gamma matrices, and you're taking the trace, and there are various sort of formulas for traces of products of gamma matrices. Just wanted to give you one example of a calculation. You might ask, well, can we see an example of, let's look at the case of Compton scattering. Let's look at Compton scattering. So some people, when they give courses in quantum field theory, they spend half the course calculating cross sections for this, that, and the other, and I think it gets very tedious. In this course, I'm trying to focus on understanding the theory behind it, what is going on, where does all this come from, what does it mean, as best as we can. But you've got all the tools now to go. If you're interested in reading ahead in chapter 8, and there's lots of different examples, processing what it calls lowest order, in other words, ignoring loops. So there are no divergences, there are no loops, there's no integrating over an unknown momentum which gives a divergence. It's a dominant contribution, you can calculate all kinds of things. If you're interested in, say, Compton scattering. Compton scattering. So there are two contributions to the Feynman amplitude that are dominant. So I have the main one that we looked at was, so I have a photon scattering off an electron, but of course it could also happen this way, that in the Feynman diagram, there's another possibility here. Prime, K prime. So you have to sum the Feynman amplitude, is the sum of these two terms, and the unpolarized, if you do the calculation, the unpolarized cross section in the lab frame. So we're going to take P is 0. Okay, the electron is at rest. So you imagine that imagine you have an electron at rest. P is 0, and I have a photon coming in with momentum. Here's our photon coming in with momentum K, and the photon is scattered. Momentum K primed, so it's scattered through an angle theta. It's scattered through an angle theta, and of course the electron is also scattered, and it has some momentum P primed. Okay, so we're in the lab frame where the electron is initially at rest. I fire a photon at it with momentum k. The photon is scattered through an angle theta, and the electron is scattered. And I'm looking at some little solid angle here to see where the photon came out. I'm working, my independent variable is the angle through which the photon was scattered. So, and I have, remember that P plus K is P prime plus K prime. So with a little bit of standard fiddling, you can derive the frequency of the scattered photon, which is probably something you did way back when you did special relativity, for Compton scattering. Okay, this is just standard, you can check again if you like, but from conservation of form momentum, it follows that if the electron is initially at rest and the photon scatters through an angle theta, if omega is the initial frequency, the final frequency of the scattered photon is given by this formula in terms of omega and theta. So we've got K is omega K, we've got K prime is, sorry, this is a 4 vector. So the 4 vector K prime is omega prime K prime, and K dot K primed is equal to omega prime cos theta. Okay, the omegas are just the magnitudes of the 3 vector. Okay, just a little bit of kinematics there, the diagram of what we're doing. What does if you do the calculation, okay, taking the Feynman amplitude to be the sum of those two diagrams, and you do the averaging and the summing over the initial and the final polarization spin, what do you get? And if you're interested, you can go through, you can follow the derivation in the book. But just to give you an example, so the unpolarized cross-section in the lab frame looks like this. It comes out to be alpha squared over 2m squared omega prime over omega squared times omega over omega prime plus omega primed over omega minus sine squared theta. This is the dominant contribution from quantum electrodynamics to the high energy Compton scattering in the lab frame. So omega is the incoming photon frequency, omega prime is the scattered photon frequency, theta is the angle through which the photon is scattered. That is the prediction of quantum electrodynamics to the dominant contribution. Then there are higher order terms in the perturbation series. But from these two diagrams, this is the result. Something of interest, just to connect with what we did before, is if you look at the low energy limit, because remember way back we did the scattering of an electron of a photon off a free electron using our low energy, using our theory where matter is treated non-relativistically, Thomson scattering. Okay, in that low energy limit, it's usually called Thomson scattering. So we should recover the same result. So the low energy limit, the frequency of the incoming photon, or if you like, the energy of the incoming photon, is much smaller than mc squared, the rest energy of the electrons. In other words, we've got h bar of c equal to 1. So omega is much less than m. So this implies from this formula, if omega is much less than m, then you can neglect this denominator, this term here in the denominator, the m's cancel, and so omega prime is approximately equal to omega. In other words, the energy of the scattered photon is approximately the same, And if you put that in here, if omega is approximately, if omega prime and omega are approximately the same, this is 1, this is 1, 1 minus sine squared is cos squared, so we get a 1 plus cos squared. This is equal to 1, so what does it reduce to? It reduces to approximately alpha squared over 2m squared 1 plus cos squared theta. And this is just exactly the Thomson scattering cross-section. I think in the book I've got a note here, equation 169a, which we derived way back. You remember we did Thomson scattering. We had an electron, we said it was in an atom, but then we said let's ignore let's treat the electron as free. We derived it way back. So we get the same results. If you take the low energy limit of this result, you recover what we got before, as we should. So you now have all the tools you need if you want to calculate high energy processes in quantum electrodynamics. If you're interested in calculating something like, well, you could do, you want to calculate 1 and 2 photons, creating an electron-positron pair, all these kinds of things, you can do this. The only thing that you'll run into trouble is when, if you start to include loops, if you start to include this sort of thing, then you'll get a divergence. But there's, as I've said, there's a way of handling these through renormalization, where the infinite part goes away and the rest is just a small correction. So this diagram here is of, remember there's a factor E at each vertex, so this is of order E squared. So the probability is of order alpha squared. If I include these higher order terms, I get an order e to the 4, and then they're higher order corrections. So the dominant contribution, you don't need to include loops. Okay, so if you're interested in calculating dominant contribution of these processes, you now have all the tools you can do. If you want to see some more examples, you can look through chapter 8. The averaging over the initial and final spins is a nuisance. It is a sort of a horrible algebraic, tedious stuff. There are some tricks that are developed in order to sort of deal with this. As I said, there are some formulas. The traces of products of gamma matrices often come up when you take these averages, and there are various formulas for those. But there you are. So I hope you've learned something about quantum electrodynamics. If you have any questions, I'll be waiting out in the corridor, or please email me office hours. This is your last chance, so if our friend here has his way, you're going to do the exam before. You sure you don't want to leave it till Friday evening, so you have more time to revise and think? Are you sure? Should we have a last vote? Who, be honest now, who would rather we just did it Friday evening? Okay, who would rather that we let this man find another time slot? All right, so okay, all right then, there we go. So I'll leave it to you. So as long as it's not Monday or Wednesday evening, but please let me know. Andrew, by the end of tomorrow. So then I can organize myself and there we are. Okay, fantastic. So good luck, and there we are.